Stanford University.
Welcome to EE380, winter 2010-2011. My name is Andy Freeman. Class boilerplate, no incompletes.
Shorter each week.
Okay. As most of you know, Python is a big deal because it's almost the nicest language. However, it is difficult to run fast because it is gratuitously meta. At almost every point, the behavior is operationally defined, or not operationally defined, but highly variable in ways that compilers don't quite like. The translation doesn't quite like. PyPy, and there have been a number of attempts to deal with this because we really would like our Python to run faster. PyPy starts with an old technique, namely self-hosted implementation, as it was called at least in one of the incarnations. It extends that and goes further with multiple front ends, multiple back ends, and I think this is close to unique, a meta JIT, automatically generating a language-dependent JIT. Cool thing. Today's speaker, Armin Rigo, has been involved in a number of those attempts to make Python fast. And he comes to us from the University of Heinrich Heine in Dusseldorf. Yes. Thank you.
Thank you. So first I will get an overview of what Python is. I mean, as Andy has told you, it's a language that is very hard to optimize statically for known tools. But why is it so? I want to give you a quick overview for well, if you don't know Python already. I mean, here is an example of Python code. Defines a class foo that has a constructor, takes one argument. The self is well, that's one specific thing in Python. All methods have an argument self that represents a this object in C++. Okay, and it has a method double that creates a new instance of the object, so return foo as opposed to new foo in Java. But I mean, and here I'm just describing some lightweight differences, and you can see that you can create an instance of foo passing it 42. Double it and get the attribute value of the result. This would print 84. Or you can have a string. Then the attribute value of this object is the string hello. And this syntax doubles the string in the sense you get hello, hello. Okay. Well, in 2 points, Python is a language.
Can you double a function?
Can you, sorry?
What if you go back a slide? If you put the double function and call it find the double function.
No, you cannot.
What
indeed.
happens?
What happens is that you get a type error.
Good.
When okay. So in 2 points, it's a strongly typed language. It's a trivially typed language, which means that there is basically only one type. I mean, if you look at this statically speaking, every variable has the type object. Very easy. But it's of course a dynamically typed language, which means basically that the type of value is attached to the value itself. And what kind of type of values are there? Well, here is some list. You have integers, floats, longs, which are integers without a bound, string, Unicode strings, lists, tuples, dictionaries, iterators, and functions and classes, which I list here in the very same list because this class or the functions that define the methods here are also perfectly regular first-class objects. And something that's maybe a bit more specific to Python is that, well, dictionaries are good, useful tools, and you have actually syntax. So this creates an empty dictionary, then set under the key I the value I times I. So in this example, we get this dictionary printed on the right. But Python is not Java, which I want to mention. It's not Java because in Python you can do this kind of things. This kind of thing, meaning here, I'm defining in a loop 3 different functions, f, and storing them in the global namespace under the name, that is a variable over which I loop. So this would be equivalent to doing 3 independent function definitions. So this is one of the tricks that you can do and that people do in Python. So well, and yes. So yes, Python is complicated. For example, a plus b works like this. This is a very simplified version. It means basically you have to look up the method called __add __ on the type of a and call it. So that allows you to define your own class, and just by putting a method add, just by putting a method add on the class, then the class becomes addable. The instance of the class becomes addable with another object. But of course, add is a binary operation. So maybe if there is no method add on the first argument, then maybe there is a method radd, reverse add, on the second argument. Okay, so all this has to be done again and again for every single a plus b in the source code. So it's slow basically, and it's also very hard to optimize. And that's it basically. So what this talk is about, I'm going to present the PyPy project. I mean, PyPy means Python in Python, as Andy explained. It's actually a framework in which you can write implementations for language such as Python. So if you have a programming language that has the same kind of characteristic as Python, then PyPy is a good framework in which to implement such a language. And so far our main interpreter is, of course, for Python. And what you get is an interpreter that is self-hosted in the sense written in itself, but from the user point of view, it's actually very similar to CPython, which is the standard Python interpreter. So to compare them a bit more, CPython and PyPy are 2 implementations of the Python language. They are both interpreters. So the first obvious difference is CPython is written in C, PyPy is written in Python. But PyPy tries to be as much as possible equivalent to CPython. And there are also 2 other Python interpreters that I will not talk about much here. The Jython and IronPython that target specifically the Java virtual machine and the .NET virtual machine. And they have slightly different goals in the sense that they want when you program with them, you program using Python, but of course you want access to the facilities of the virtual machine as well. So the PyPy project, PyPy is some experimental project, let's call it, that was started in 2003. It is an open source effort of volunteers. I mean, a group of volunteers like 5 or 10 or 15 people over time. It did get some funding support, I should mention. It did get 2 years from the European Union, and now it's running from money coming from the countries of Germany and Sweden. It is, well, the way we develop it is really test-driven. So we have 200,000 lines of code roughly, and 150,000 lines of code of tests. And well, to compare a bit, maybe for some of you may know, the other kind of self-hosted interpreter. I mean, the most well-known example is Squeak, probably. There is also Scheme 48. So there are like PyPy, there are a version of the language, let's say Smalltalk in the example of Squeak. It's a version of the language that is implemented in itself, but well, not quite, because it's actually some subset of itself, which is the same as PyPy. However, one difference that I will explain then is that in the kind of project like Squeak, they are implemented in Smalltalk, yes, but it's a very restricted subset of Smalltalk. It's a subset of Smalltalk. Well, I would say it's mostly C code with a different syntax. But PyPy is written in RPython, and the language RPython is much higher level than that. So the goal was really that every single aspect of the interpreter that we want, well, every aspect that is somehow independent on the detail of the language that you interpret should not be written explicitly. So memory allocation, garbage collection, the details of the object model, all this is not present in RPython. Okay, maybe a quick view. What is the point of PyPy then? First question. Because CPython is an older existing official version that works very well. And PyPy is just a replacement, so why? And then of course, as usual, when you come with this kind of project, well, PyPy is not even a complete replacement, because there are some features like C extension modules are only partially supported in PyPy. Okay, well, the main answer is PyPy is faster. And it may use less memory, okay, but mostly it is faster in the command case. And here I prove it basically.
Proof by example.
Yes, here is a number of real-life benchmarks, and the bold line is at 1.0. That's time normalized to CPython, some version 2.6.2, and well, you can see that we are at least 2 times faster generally for this kind of benchmarks, and this it can be 10 or 20 times faster, and there is actually only one that's 1.5 times.
Is it any good reason why that is slower?
Yes, because it's using crazy things. I mean, yes, well, mainly what we did is try to optimize for the command case, of course. And this is just using all the time some completely crazy things. So this was the main point of PyPy that we have right now, but there are also some smaller benefits of PyPy. Is that you can have a number of features. You can have stackless, of which I will talk maybe a bit later. You can have non-Python interpreters because, well, you can, how should I say it? You can write an interpreter for any language that is similar to Python. Like, for example, we have interpreters, well, toy interpreters, incomplete interpreters, but we have them for JavaScript, Smalltalk, and Prolog, for example. How?
Are these toys also faster?
Prolog is, yes. So the others we didn't finish them enough to know. Well, basically it's a better experimentation platform than CPython, or than writing in C, basically. If you have some language that you want to play around with, well, PyPy is a better platform to try it than just having to write in C. And this is a negative slide. It's one of the known issues of CPython right now is that it's not really multi-threading. I mean, it can start multiple OS level threads, but then there are well, only one of them actually runs at a time. So it does not help in the case where you really need multiple processors. And PyPy has no answer. It has the same issue. So, as I said, PyPy, what's the architecture? I'm going to dive a bit now. PyPy has two parts. It has a Python interpreter which is written in RPython and some compilation tool chain that translates this RPython code to C code. Okay, the interpreter is kind of looks like CPython, but the difference is that it's written in RPython instead of C. Well, it's a difference that we make use of mostly for testing, for example. If you write we have written our interpreter in RPython, but then it's also valid Python, so that you can actually test it just by running it on top of CPython. So that means, sorry, if I, sorry, I'm sorry. Hello? Ah, okay. Ah, I see. Excuse me. Okay. Okay, this starts PyPy with, well, a few warning and error messages. This is running PyPy on top of the CPython interpreter. And then you get a normal prompt that has 4 greater than sign instead of 3, if you know. And well, you can do things. 10 print I. Oop, okay, so you have seen that. Well, we actually see that we saw them coming one after each other. It's very slow in this mode. It took something like half a second to do this simple loop. But it's a complete Python interpreter. I suppose, however, we didn't try actually. Yes, we tried at some point, indeed. Yes, it takes only about 3/4 of an hour to start. Yes. Okay. Yes, yes. Okay, the other point, so this was one aspect of PyPy, it's Python interpreter written in RPython, and then the other point is the translation tool chain that can take some program written in RPython, for example an interpreter, and it outputs the same program written in C, same in quotes. So if I want yes, so here is an example of a program. It is RPython, trust me, it's also valid Python. It defines the class foo, very similar to the one we've seen already, and the function main taking argv. Notice it looks a bit like C already, and gets a number n as the int value of the first argument, or 22 if there isn't any. It makes a list of instances of foo, and it prints the last item of the list, double value, and returns 0. Okay. So with this program, no. Yep, I'm sorry, I don't see what is here on my screen, so it's not completely convenient. Demo 2. Yes, so this is the translation tool chain. Takes and analyzes the program, and in 4 seconds give us this program Python demo 2 C that works. So it takes the last element of a 100 items list, which in this case has the number 99, and prints the double of this number. Okay, so an important point is that well, RPython is still valid Python code, which can be tested directly. You can really take my example demo 2 and run it, and well, there are some restrictions. I mean, it's called RPython instead of full Python for some reason. So you need some type safety. This translation process needs to be able to make sense of what is going on in the program. However, RPython is still a high-level language that contains, for example, no garbage collection detail. Like there is no. I mean, the example PyIncref and PyDecref are macros that are used everywhere in the source code of CPython, and they just mean increment or decrement the reference count of this object, because CPython is a reference count based implementation, and you cannot change that because you need to change everything everywhere. Well, I mean, from one point of view, why did we define this new language RPython instead of using, for example, a language like Java? Because it's a bit similar after all. You have the same kind of level. Well, the difference is in the last sentence. You actually can use a lot of tricks in RPython that you cannot use in Java, and this is really useful for the task at hand, at least, which is writing interpreters. That's the first example for why it's useful. That's the most important example, I would even say, is that well, RPython is a restriction on not the source code of the language. If you take the source code of the language, you cannot decide if it's RPython or not, because what we do is import the RPython code normally in a Python interpreter, and then at import time you can do whatever you want. Like, for example, the creation of functions in a loop, sticking them around, and so on. And this is really useful for writing an interpreter, for example, where you have a list of not only 3, but 20 or 50 such operation names, where you need to do something similar. So in this example, the function f has, well, you want the code in the function f to be RPython, which means well-typed and safe. But of course, the loop around does not need to be RPython at all in this example. Okay, so from there, I have 2 different set of slides. So I would like to have some input, basically, from the audience about which set of slides you are most interested in. The first is the interpreter, where I'm going to describe in more detail various things that we did in the interpreter, and there are things that we could not do in CPython, for example, mostly because it's much easier to play around writing RPython code than writing C code. Okay, and the second set of slides is about the translator. So everything the detail of how we translate this RPython code to C code, and I mean, the important points of the translator is how we insert aspects like garbage collection, or the object model, or the just-in-time compiler, for example. So, any preference? I mean, you want me to go more in the direction of the just-in-time compiler, for example?
We've done it at 5:30, so. Yeah, let's hear out the jet.
Okay, so we can always come back here. So let's switch to this part. So the translation toolchain in a few words. Translation toolchain is, well, as I explained already, the important point is that every aspect of the final interpreter that you want to keep a bit orthogonal from the high-level description, we don't write it in the high-level description. Instead, we write it as aspects. I mean, I'm using here the word aspects, not in the official, in what is now the official sense, but instead in the original sense of aspect, which is that they are, how should I say? There are some functionality of your source code, of your code, that gets inserted by some other code. Okay, so to translate a program, well, to translate a program we do a lot of different steps. The first step is to, well, you have this RPython source code, so we get the control flow graphs. So we get the control flow graphs of every function in the source code, and and from this family of control flow graphs we perform some global type inference. So the global type inference may not succeed, of course, if your program is not valid RPython. But basically, that's the definition. Your program is RPython if this global type inference succeeds. So in this, yes. Okay, so it's the same example as before. Yes. So this is control flow graphs. Here we have 5 control flow graphs. The first one is the main function that we had before. The second and third are 2 methods on the class foo, and the last 2 are to implement print, actually, where we print the result. And you can see, if we zoom a bit, this is actually, well, here we see the source code, and this is expressed as a list of operations, and every operation is at the level of Python of the source code, basically, where the first thing is take this argv, ask for its length, ask is it lower or equal than 1, is the result of this comparison true, and then 2 cases, and so on. So this is the control flow graph, equivalent of the function. And here we already performed type inference. So that means, for example, if we have this variable, yes, this is a variable n, and here it says that n is some integer. So it found out that n is some integer. And how did it find out? Well, this is abstract interpretation. Basically, you start with from the beginning of the function and found out, oh, this n comes from the length of something, then it must be an integer, and so on, and follow all calls. And in this way, you eventually get annotation for the complete program. Okay. Okay. Yes. Okay. So from there, you generate more code. Now, what you actually do here we see again the shape of the function we were looking at, and what has happened here is that every single operation has had its level lowered. So before it was len of args, I mean v0 equal len of argv, but now, well, argv is a list, right? So how do you compute actually the length of a list in C code? Well, you need to call some helper function. And similarly, this was lower or equal. Now it's precisely integer lower or equal. And for example, this was typed as a list of strings, and now it's a pointer to a structure called list. So this is at the level of C. Okay, so here we did the first point that I explained here. The level of the control flow graph transforms the Python-like operation to C-like operations. And well, basically from this we can generate C code that corresponds obviously to the control flow graph. However, the interesting part is what we can do in the middle. We can take these graphs and transform them. We can transform them in various ways, and these various transformations are what I called aspects previously. So these are the 4 main examples of such aspects. Well, the first is the object model. How do you turn something that is as complicated, well, as simple, I would say, as simple as a class and instances of a class. Okay, but that does not exist in C, and particularly if you have subclasses and then you want to call a method, but which exact method is going to be called depends on the exact class of the instance, etc., etc. Well, you need basically a way to lower this into a representation that is using structures and pointer to structures. Then the second aspect is garbage collection, because the source RPython code definitely has no explicit garbage collection. So it means that if we do the transformation as I've showed you so far, we get a version of the code that can still have an operation saying, here, create me a new instance, but it will never free it, never explicitly. So with this transformation, we transform this abstract allocate something operation into a call to some GC, some garbage collector. There is another aspect, it's the execution model. We can use regular or so-called stackless execution models. The stackless execution model is called stackless because it's a model in which in the C equivalent, you are if you take a simple example of an interpreter, the interpreter may be, of course it depends on the details, but the interpreter may be written in a recursive style, which means that every function call that you do in Python is implemented by recursively calling the interpreter from itself. And so if you do that, and in the regular translation model, you translate this into a recursive call at the C level as well. So the stackless execution model corresponds to you do a transformation that allows you to write C code that is no longer recursive. It involves basically saving away and restoring the state of the local variable. And that's how we can support, for example, stackless Python, which is a fork of CPython, and which needs a lot of supports and a lot of various changes here and there in CPython. Here we support stackless Python out of the box just by applying or not this transformation. And yes, and the last point is a just-in-time compiler, which I'm going to talk about now. Yes. Okay. So the point is that our just-in-time compiler, of course, the goal is to speed up the interpreter, which is written in RPython. But the interesting point of the approach is that we get a just-in-time compiler that is independent of what is the language that the interpreter runs. So let's call it a P interpreter, where P is, for example, Python in our example. So basically, I'm going to describe how you get a JIT compiler for the P language, for whatever P. Well, what is a JIT, of course? A JIT selects pieces of the user program that pieces that would benefit from being turned from not being repeatedly interpreted, but then the pieces that would benefit from being turned into machine code, of course. So the traditional, when we talk about JIT, we traditionally have Java. Java is the most well-known example of JIT. However, it is the modern terminology is that it's actually a method JIT in systems like Hotspot. And the method JIT, takes your function, your P function, like your Java function. So it takes the P functions that are often executed or that contains loop or something, and it compiles them. And maybe it does some inlining to improve performance and so on, but the basic compilation unit is one function. And a more recent approach that we use in PyPy, this is the approach of tracing JITs. And in tracing JITs, it's very different actually. it finds loops in the user program. So it monitors the execution of the user program, just like a method JIT, but it looks for loops and it compiles a loop. But one execution of one loop is, well, it means, sorry. Well, the main difference is that what you get in the end, you get a completely inlined trace, basically. If you trace the execution of one loop, it means you follow what the interpreter would do to execute this loop. And that includes all calls to all helper functions. And you get a big linear trace, and you compile this trace as a loop of machine code. So this is the basic approach of tracing JITs that is used, for example, in TraceMonkey for JavaScript and in PyPy. So more precisely, we run the user program, we do some lightweight profiling, we profile mostly the loops, and when a loop is run often enough, we enter a special mode. The interpreter enters a special mode in which it records, in addition to doing the next iteration of the loop, it also records what it does, and in this way produces a trace that contains everything. And then, then you compile the trace to machine code and you execute it immediately. Yes, of course, the machine code. Well, if you do just what I described, you get an infinite loop in machine code. But of course, the loop contains words. It's for every decision point in the interpreter. For every decision point, we record. Well, we record that the interpreter checked this, for example, checked this value. And in the machine code, it's called a guard, but it's actually just a conditional jump. And if the condition is no longer satisfied, then the conditional jump is taken, and then we do something like we recover and go back to the interpreter. So what I described so far is tracing JIT, which is the standard approach nowadays. However, in PyPy we have meta tracing. If you want to implement what I just described for a language like Python, well, it's a lot of work. You need to support all operation. You need to do something about the addition, the four cases of addition that I described at the beginning, or you need a lot of work, basically. However, we have a meta tracing JIT in PyPy. That means that we didn't do the work of implementing the JIT compiler for the Python language. Instead, we implement it only for RPython, and we are tracing not the program written in P, but we are tracing the interpreter that is itself interpreting the program written in P. So basically it's portable. It works whatever the language that the interpreter interprets is. Okay, and here I have another demo. So it's an example that is a bit bigger, because I wanted to actually show the kind of issues that we have in a dynamic language like Python. So here is an interpreter for a language that assume this is Python. I mean, it contains a base class object and two subclasses, integer or string, and they both integer and string have a method next that does something different. A string just concatenates a character, and in integer it adds one. They have a method small that checks if some bound is reached. Okay, and this is the full interpreter. It interprets a bytecode. Bytecode is a string of characters. Interpret it by looking at every character one after each other. Here, and if it's a character n, it just calls the method next on whatever input it got. And if it's the bytecode L, it asks if the input is small, then PC equals 0. It means I jump to the beginning of the bytecode again, so I make a loop. Else, if the input is no longer small, I just return. So, for example, this program, you can just run it, and if you interpret something like NL, L being the loop, on a string or on an integer, you get different results. I can show you. So I run this program. Okay, it runs. Bah. Yes, indeed. Yes, I don't have power. No, it's plugged in, but it's not getting power. Sorry. Is there a switch? Okay.
That should work.
Okay. Yep, sorry. Okay, so this printed, well, did 2 prints with a string x whose limit to being small is 50 characters, and this with an integer whose limit to being small is 1 million. So you can see, I mean, the point of running this is to show here how much time it takes to reach 1 million in that example. So it takes something like 4 seconds to reach this number. Okay. Right. I'm sorry. Yes. Okay. So the first thing we can do is we write this function main, and then we are going to translate the code above, of course. So then we are going to get a program that takes 2 arguments and works only on integers, let's say. That's good enough for this example. And if we translate it, we get demo. So let's say this loop from 1. Yes. Sorry. Well, yes, okay. Yes, sorry. That's a 32-bit translation, and here I'm in the 64-bit environment, so no way it will work. Well, okay. Basically, we run this and we get the same output, 1 million, but much faster because it has been translated to C code. Okay, if you trust me on that. Mm-hmm. Yes. But that's not the end of the story. The point is that from here we can use the JIT to actually do something about this interpreter, because from up to here we can translate it to C, okay, but it's still C that will create an instance of integer at every iteration of the loop, and then call the garbage collector to reclaim all these integer instances and so on. So what do? We add this line and this line, two magic lines. Well, basically we add this line here as a way to guide our translation, to tell it, oh, this particular loop in which I put JIT merge point, it's really the loop of an interpreter. So look closely and please give me a JIT corresponding to this interpreter. And, well, same as before, you have to believe me. When I do that and run the JITted version, it's faster by about 14 times. Mm-hmm. So yes, so that's what we did with the complete Python interpreter. We just added one line. Well, mostly here I'm cheating a bit. We added essentially one line. But yes, the point is still that you add maybe 20 such lines at subtly chosen places, and then you get a JIT for the interpreter. Mm-hmm. So what kind of JITs do you get? Well, the idea is that, well, you run the translation, so you get the control flow graphs of the interpreter. So in order to be able to do something with them later at runtime, when the JIT works, you need to take these control flow graphs and somehow flatten them into some kind of bytecode representation that we call JIT code. Okay. And then, well, you have the JIT that is written in RPython. We have this JIT written in RPython, and we have to link it somehow with the program, for the P interpreter, for example, that I showed before. And you add some lightweight profiling code and so on. So here I'm describing what's the well. This is something that occurs during translation. Mm-hmm. But then at runtime, you measure some profiling, and then when you reach some threshold, then you start tracing. So you enter a tracing mode well, what are you going to trace? You are going to trace the interpreter interpreting the program. So that's why you need the JIT codes. So you take the JIT codes, that is the representation of your interpreter, and interpret these. So you are interpreting the interpreter interpreting your language P, right? So the point, of course, then while doing this double interpretation, you can record every single operation that occurs in the interpreter. And in this way, you build a trace that is really a low-level trace that will contain all details of how you must interpret your program P. So of course it's slow because it's double interpretation, but then it's not that much of an issue because it only runs for one iteration of the P program. So maybe 10 or 100 iteration of the interpreter interpreting one loop in the P program.
What about conditional? You don't get the trace from conditional branching in tank.
Yes. You only get the condition as a guard, and then. There is a. Sorry. Okay, so about the condition that existed in the original interpreter as trace, just as is usual with a tracing JIT. So you get a series of words that checks at runtime that the condition is still met. So basically you get a trace that means a linear sequence of operation always in this way. So from this linear sequence of operation, well, then we have a machine code backend that turns it into machine code, and we have so far it can be x86 or x86-64 or in progress ARM, and yes, all guards are compiled into conditional jumps. And if the condition happens to be false, then jump somewhere else, and the somewhere else will do the recovery job, basically. And the point is that we need yet another interpreter in this approach, because when a guard really fails, we don't know where to go, basically. We cannot jump back into the original interpreter because, you cannot enter a C function from the middle, basically. So the solution that we took is, you use yet another interpreter that we call the black hole interpreter for some historical reason, and the idea is that you interpret again the JIT code until you reach a state where you can really jump back to the real interpreter. Yes. This I described so far one loop. So that's a very simplified example where your program is actually doing exactly the same thing at every iteration of the loop, but of course it's not the case in practice. In practice, you have typically one loop in your user program is at least going to follow 3 or 4 or 5 different paths often enough. Well, it depends, but usually it is. So what we are doing is the so-called bridges. So when a guard fails often enough, so we just have profiling on the guards. When they fail often enough, we start the whole thing again. Basically, we start the meta tracer optimizer, generating machine code, running the machine code from the place that contains from the location of the guard failure until the next iteration of the loop. And in this way, we generate branch after branch a complete tree of operations. And okay, here are some other topics that I could talk about. I see that I also skipped this slide. This slide explains what is going on between, yes, sorry. That's also something that I wanted to show that I cannot. Once you get the trace, there is actually an intermediate step between getting the trace and turning it to machine code. We can once you have a trace, the trace records a complete loop. So then you can do some optimizations on it. And some optimizations are really effective. I mean, the most important optimization is the escaping analysis. Because in a typical interpreter, you have some operation like, I mean, let's just look at the interpreter here. If you do an n operation, then you are going to take this, that is, it's a boxed object, for example, an instance of the class integer. Then you are doing this method call, and it returns you a new instance of integer. So, for example, if your bytecode contains n, you're going to make two intermediate pointless instances. So in that case, the trace is going to contain all the operation. It means it's going to say, here I allocated an instance, then I filled its field with some value. Okay, and that was one bytecode. Then the next bytecode, I read again the instance, then I forget the instance, and I create a new instance, and so on. So all the intermediate instances can be removed then by this optimization, just by looking at the trace. So this is essential, basically. That's where we gain the most performance. For example, this example gets 14 times faster, as I explained. This is mostly because we remove completely all GC pressure by not needing to allocate all instances. And this is a common situation in a language like Python, because every operation creates a new object that is the result of the operation mostly. So this was escaping analysis. I can also talk about all the other kind of optimizations, like integer bounds. Integer bounds optimization just verifies, oh, here I have this integer, and I compare it with 3, for example. Here I check that it's greater or equal than 3. Then later I check again that it's greater or equal than 2, for example. Then we know it's true because we knew already that it was greater or equal than 3. This may look like a completely artificial example, but actually it's not. It's not, because such checks are actually common. Because simply, I mean, so it's simply because they are from different parts of your original interpreter. I have this P interpreter. One check comes from interpreting this bytecode in this situation, and then the other check comes from interpreting this other bytecode. So that, well, we can see both checks and optimize them only at this level. Then store thinking means it's the optimization that delays. I mean, it's for the case where escaping analysis does not work and we still need to allocate the objects, then we can delay writing into the object, because commonly we allocate an object, then we write some initial value on the fields, and then in the next bytecode we are going to write some other value in the same field, for example. Then here we delay the writing of the field values, and we can do it only once. String handling, it's another example. Like we have this small string, and you write code that adds one character, I don't know, something. You have this string S, you add one character to it, and then a bit later, if some condition is true, you add another character to it. Then if you look at the complete trace, well, you see that you can actually optimize it and add directly the two characters, and they don't need to allocate the intermediate string. The FFI calls, FFI means foreign function interface. That's all calls that you do to well, via the foreign function interface, which is called ctypes in Python, for example. I mean, that's one of the interfaces existing in Python, where you declare and call external functions written, well, that come from C libraries, for example. It's the case whereas the function that you want to call, well, it's a call to a foreign function, which usually is implemented by going to libffi, if you know it. It's a library to call a dynamically built function. So here we can actually reverse the dynamism and say, I have this trace where I see that it's obviously this function that gets called, so I'm going to generate assembler that directly calls the C function. And yes, well, I can go on forever basically on this.
You have 10 minutes.
Thank you. Well, yes. So basically, I mean, the main point I want to say is that, well, these are all examples of optimization that we do. I mean, these are all optimizations that are completely independent on the detail of the P language that we interpret. These are all optimizations that occur whatever P is, as long as you write it in RPython. So, well, we wrote here in PyPy the first ever meta tracing JIT. And yes, some extra topics that I could go into forever. Maybe I should mention the last topic, which is somehow important from a user's perspective as well, is that it was actually easy to add memory management of the generated machine code. So the pieces of machine code that get compiled into assembler are also memory managed by our garbage collector. And so if they are not used for long enough time, then they are going to be freed. And yes, and well, in general, because this is a tracing JIT and not a method JIT, the number of traces that we compile is actually relatively low. So that's why we could, well, that's why I'm describing here all these, for example, all these complicated optimizations that we do on a trace. Yes, that takes time to do all this optimization, and I mean, I can measure the time, for example, to 10% of the total runtime in some examples that would take 10 seconds of runtime, for example. But that takes time. But well, we win it at the end because we have a small number of loops.
So what sort of code expansion do you get as you do execution?
The code expansion we don't know, we didn't measure. I mean, if you're talking, well, we never have a complete code a complete JITed version of everything in this model. Never. You just have the pieces of the particular loops that are running now that gets compiled and that may be thrown away later if the loop really no longer runs at all. I mean, I can give an example of measure of a real program. The program in question is translate.py that you have seen running already. I mean, translate.py running on top of, well, translating the complete Python interpreter with everything included, the JIT, etc. That's an operation that takes about 1 hour of runtime and 1.2 gigabyte of memory on top of CPython. And on top of PyPy, it's twice as fast, but the memory is something like 1.7 gigabyte. And in this 1.7, we have about 200 megabytes that are really used by the JIT.
And the advantage of using the trace mechanism as the selector for what you optimize is that the optimization has no flow analysis necessary.
Yes, that's one of the
That's a big win because it makes for much simpler optimization code.
Yes, it simplifies a lot of optimizations, but it also enables a lot of optimization because if you try a standard method JIT on this kind of project, you lose basically because every single operation like a plus in Python, it becomes a complete mess of decision tree. So yes, I mean, as opposed to in our case where we follow just one path, and usually it's a short path.
How do you interface with extension modules for C?
Well, there are several ways. I mean, the most interesting from this talk's point of view is indeed that we can use C types. So it's a standard way that exists also in CPython, in which in pure Python you just declare as external functions. You declare as external function all functions that you're interested in some C library, and then you call them. So this is implemented in both CPython and PyPy. Actually, this is implemented using libffi, which allows to do exactly that. So this is an answer to interface, an answer that would be very bad if we were talking only about CPython, because it's horribly slow, of course. However, in the case of PyPy, we can make it fast again with one of the optimizations that I described, the FFI calls optimization.
Is there any interaction between this project and TraceMonkey, except that you're sort of on the same goal?
No, there is no real interaction, no. I mean, the main difference is the level meta tracing versus normal tracing.
What about the Python 3 support?
So Python 3 support, well, we don't have it so far, but we upgraded to Python 2.7 now. It's almost there, so that means that it's not very far, basically. Well, I mean, the Python 3 support will be one day written by tweaking the interpreter, but the RPython code will still be a subset of Python 2, likely. So it means that we will stop being a self-hosted implementation, which does not really change much.
The other way of going meta is that in partial evaluation, you've got an interpreter, but you know what program it's running. So you can specialize your interpreter for your program. But when you do that, you also mentioned that you have to occasionally insert directives, but people are horrible at inserting directives. With a little bit of flow analysis, can't you predict the right traces to do?
I see. Well, I suppose you're talking about this JIT driver.JIT merge point line.
Yep.
Yes. Well, yes. I mean, here we are already incredibly good in the sense that we just need one line, I suppose.
Yeah, but it's typed by a human, so it's wrong half the time.
Yes. Well, I mean, so that's really going to the details of the JIT. I really think that it would be possible to do it with zero hints. But yes. Well, so far for convenience. Yes.
How far away do you think this is from being ready for production use?
Yesterday. Yes, I think it's basically ready for production now. We have, I mean, the exam. Well, well, we already have the speed benefits that I showed, and then Python, well, PyPy version 1.4.1 has been around since December last year, and no bug has been found. Basically, it's a really stable platform, which is good, I suppose. It also shows that our approach to generating a complicated JIT is actually working. I mean,
Timeline for getting all the standard Python modules supported,
well, they are supported.
like everything in the standard
Mostly,
library.
yes. I mean, they are mostly supported, but well, nowadays we are working on Python 2.7 support, and then yes, I think we support most of the standard Python C extension modules. And we have also already a module that tries to import C extension modules on top of PyPy.
How does your translator from RPython to C compare to Pyrex?
So how does the translator compare to Pyrex? Well, Pyrex is Pyrex is a language in which you write explicit type annotations here and there. You have to declare your variable as typed integer, for example, and then it produces a version of this in C code. I mean, the difference is that in our approach, the translator is a much bigger tool. First it works without any annotation, and it's capable of finding really good types, like this is a list of integer, and so on. And then the main point of our approach is all the various aspects that we can insert, like garbage collector support, the JIT, and so on. All these are aspects that we can insert, and this is something that Pyrex does not do. Yes, I want to show this page. Yes, the last line in particular, there is a sprint as nose bridge going on this weekend. So for the 2 days of the weekend from 10 a.m., where everybody is welcome. Yes?
Let's see, you're 8 years in, you have 200,000 lines of code in the system. So that's essentially 2 full-time equivalents for 8 years. That seems a low level of productivity given the amount of manpower that's been gone into it for all these sprints.
No. I mean, yes and no. I mean, you cannot measure productivity just by the amount of lines of code. I mean, when I say 200,000, it's measured today, but actually we did a lot of more experiments and threw them away. And
So how much code did you throw away?
I don't know. Yes, I see the question.
200,000 lines include the code for the sources or for the tests as well?
No, it's
That's a separate,
yes.
separate package.
That's another 150.
So that's 50,000 lines of code. So John, it's really 350,000 lines.
What do you mean unproductive? It's standard measure a line a day a person. So that's 300 lines.
6 instructions.
Yes.
Another way
I'm not
of
sure I understand because
metacoding. So it generates about how many lines of C code?
120 megabytes.
But there your value was one number, it's wrong with the 5 number.
Yes, so in our 8 years project, just an open source project, we wrote a 120 megabytes of C code. So we have good value.
At 350,000, this is one of the larger Python projects in the world.
Yes, that's true too.
So, how, most Python projects run into problems somewhere around 10K. Why didn't you?
Let's see. Yes. Yes. I mean, it's large and complicated, basically. I mean,
I agree that to some extent the complexity of our translation toolchain is a bit overkill sometimes. I mean, it used to make sense for some experiments that we did, definitely.
I'm curious, if you compare PyPy to optimization, then how fast, in principle, do you think you could go? Would it be 5 times slower, 10 times slower, 2 times slower?
I see. Well, if you look at the PyPy blog, there is an example where we are faster than C. But yes, that's just one example. I mean, in general, it's also true. Well, what should I say? This approach, well, if you take the speed of a language, you try to talk about the speed of a language, then you have C and you have Python, and where we are going with PyPy is in between. I think really in between. And yes, I mean, it's also it's sometimes a bit of a drawback to have our JIT being actually so completely general, because occasionally we could if we were writing the JIT by hand instead of generating it, then we could write this optimization here for this special case, and in this way get a bit better. That's one issue.
We're not done yet. We have lots and lots and lots of more optimizations to make. It's not like we're finished and it's time to measure and see this is the best we can get.
And that's exactly my question. Say, if you implement everything which you have in mind, what would be your guess as to the final performance?
I think it's too early to be. Our breakthrough, when we went from being about 2 times slower than CPython to actually being able to do this, is only about 8 months old. So we don't know yet. We haven't really been able to look at the details of the behavior of the code.
Plus, we have a whole bunch of crazy ideas, and no one's ever tried to optimize them like this before. And we don't know whether they're going to give wonderful speed-ups or we should throw it away because it was a bad idea. We've already thrown some idea away, but it's really hard to predict things that way.
Can you keep a list of the ones you've thrown away?
Oh, yes. We document everything.
Well, in the optimizations that you do, what of them are unique to the PyPy project, and what are adaptations of other people's concepts of optimization?
Okay.
Yes, the kind of optimization that our JIT does, for example, is, well, I really think that we are doing much more optimization than all other JITs. I mean, the escape analysis, I think that the JITs for other languages are also getting there now, but that was our starting point, actually.
I take your thing. We've lost the remote people, which is just the way it goes. So we can keep going.
For more, please visit us at stanford.edu.